All right, recording for this Zoom session. What we want to do today is finish off Unit 2, the intensity and the decibel, and then we'll start in on Unit 3, which is complex sounds. So we all recall, and I guess, just Unit 1 basically was frequency, wavelength, speed of sound. And in good old Unit 1, there's two sets of formulas that you really needed to pay attention to and understand, and that was period is 1 over frequency, frequency is 1 over period. And then the second set of formulas from Unit 1 was the speed of sound over the frequency, and then you did that to calculate the physical wavelength. Not the period this time, but the actual physical wavelength. So wavelength is speed of sound over frequency. And speed of sound always is constant in air. It's the same for all frequencies. And that was basically the two sets of formulas from Unit 1. And both of them, okay, one's dealing with period, the other one dealing with wavelength. And both of those are inversely related to frequency. In other words, the higher the frequency, the shorter the period. The higher the frequency, the shorter the wavelength. Okay, that was Unit 1. Unit 2, we covered the decibel from hell, and we talked about all kinds of things, but starting basically, we'll take a running jump at it. Look at page 1. Make sure you know what pressure means. It's force over an area. Make sure you know what power is. That's work done. And make sure you know that the decibel can be either measured in decibels sound pressure level or in decibels intensity level, which is power. So some people use the thermometer of power, some people use the thermometer of pressure. But I showed you last time too, and 2 weeks ago, that freezing is freezing is freezing and boiling is boiling is boiling. Okay, and so in the USA, freezing is 32. In Canada, freezing is 0. In the US, boiling is 212. In Canada, boiling is 100. Okay, but you put your hand in a pot of boiling water, you're going to burn your hand either side of the border. Okay, so all I'm telling you is the softest to the loudest you can hear can be measured in terms of power or pressure. All right, and then we moved on and said we prefer pressure because the ear works as a pressure receiving device. So forget power. Okay, and we also said that power, the softest power was 10 to the minus 16 watts per centimeter squared, and the greatest power we could tolerate was 10 to the minus 4 watts per centimeter squared. And the difference between those two is 10 to the 12, and that's a trillion. If you have a 1 with 12 zeros behind it, you got a trillion. Okay, so the softest power compared to the loudest power you can tolerate is a trillion times that of the softest power it takes to just barely hear. And now go to pressure. What's the softest pressure it takes to just barely hear? And now I'll share screen and we'll go to that particular photograph and make sure we've got that puppy down, okay? So let's go to it here. And we'll pull up this guy right here. And once upon a time, there was a bunch of people sitting around that had nothing to do, and they said, hey, let's measure sound intensity. All right, let's choose pressure. And they said, what's the softest it takes for a normal hearing human to hear a 1,000 hertz tone at 1 meter distance from a speaker with 2 ears? And they found that softest pressure against the eardrum was 0.0002 dynes per centimeter squared, because pressure is force over an area. And they called that 0. And that's what we're circling at the bottom left here with my cursor. And if they increase that pressure by a factor of 10, now you're at 20 decibels. And if you increase that pressure by a factor of 100, you're at 40. And if you increase that pressure by a factor of 1,000, you're at 60, and so on. So the greatest pressure you can tolerate is 1,000,000 times more than the softest pressure it takes to just barely hear. All right, cool. So there's that, all right. But again, call this boiling and call that freezing. So how come this is only 1,000,000, whereas in power it's 1 trillion? Well, Power equals pressure squared. A trillion equals a million times a million, okay? And remember, the thermometers are just different. The height between isn't. It's the same. It's just that when I'm using power, I've got way more increments in between. All right, and just look at water freezing, water boiling. I just use this analogy constantly. But go to pressure, and you can see that you've got fewer units, but the decibel distance between the softest and the greatest is identical. Okay, and the point to take home is that the range of intensity required that for us to hear from barely audible to screaming pain, that range is whoppingly huge. And we can't deal with such a huge range. We need to shrink it down into a manageable range, and that's why we use logarithms like your textbook has done. And that's why 120 decibels is really 1,000,000 times the pressure against your eardrum as 0. Okay, now we've hammered that point home, and we can talk ad nauseum. Let's move on to the bottom of page, or the middle of page 3. And you're in the middle of page 3 in your intensity unit, and we talked about doubling the sound pressure level. And we said if you take a 1,000 hertz tone of, let's say, 40 dB SPL, and you add another 1,000 hertz tone at 40 dB SPL, the sum total is going to be 46. It's all because of those stupid logarithms. It's not 40 plus 40. Please don't do that. Okay. Now, that's if you double it. If you have a 1,000 hertz tone and you add 9 more, so now you got 10 1,000 hertz tones at 40 dB SPL. One tone was at 40 dB SPL. Now you've got 10 1,000 hertz tone at 40 dB SPL. Well, now you've gone up 20. Now you're at 60. Okay, because 40 plus 20 is 60. And I've increased my sound pressure by 10-fold. Before I had 1, now I've got 10 of the puppies. Okay, so 10 times the sound pressure level, I've gone up 20 dB. And that's what we can say here. Basically, when you're looking at your good old notes, and you move on down here, and you can see if you increase the pressure by a factor of 2 to 1, you've gone up 6 dB. If you've increased the sound pressure by a factor of 10 to 1, you've gone up 20. Okay? And so put a star by the 2 to 1, the 10 to 1, and put a star by the 100 to 1 sound pressure increase, because that also corresponds with this picture over here. Okay? If I've increased my pressure by a factor of 100, I've gone up 40 dB. And you'll see that right here. Okay, if I've increased my pressure by 10,000 or 100,000, etc. Now you get the picture. And then we said last week, but in real life, we're not normally adding tones of equal frequency and phase. Usually the sounds are different. In other words, what happens if you have a 1,000 hertz tone at 40 dB SPL and a 2,000 hertz tone at 40 dB SPL? When you put those together, you don't come up with 46. Now the number's 43. So if the two tones are equal in intensity, 40, for example, but they're different in frequency, then you only go up by 3 instead of by 6. Okay? And now let's take that analogy home and look at what would happen in terms of a choir. You have one person singing, and then you have 100 people singing. And if one person sings at 70 decibels SPL, and now you have a choir of 100 people singing at 100 dB SPL. Okay, what's the total overall intensity? Well, first of all, remember the people are different. They're not the same. Okay, so normally when you increase the pressure by 100-fold, you've gone up by 40 dB. But that's only if everything is identical. That's if you had a choir and now you have 100 clones of the same person. Then you'd be going 70 plus 40 is 110. But the fact of the matter is there's no such thing as human clones. Okay, we're all different. So because we're different, instead of 100 people increasing the pressure by 40, now 100 people increases the pressure by 20. Just like 3 is half of 6. If the tones were identical, I went up by 6. If the tones were different, I went up by 3. That's if I doubled things. Okay, well, talking about 100 now. Instead of doubling, but instead of 100 being an increase of 40, 100 now is an increase of 20, just like 3 is half of 6. So if I ask you, or when I ask on a quiz or a midterm, okay, promise, so put a star by this, make dang sure you got this thing down, all right, because it's the essence and purpose of the decibel. It's just basically knowing how to negotiate your way around and through the decibel. And then we had another wrinkle to it, because look at the top of page 4. In real life, we're not always adding equal values together at all, not just in terms of frequency. Not only are they different in frequency, but in real life, they're also different in intensity. Okay, this is the next wrinkle. So now you may not be doubling the sound pressure or increasing the sound pressure by 10-fold or 100-fold with different people. But now you might be having, what's a 90 dB SPL sound plus an 80 dB SPL sound. They're of uneven, not only uneven, different in frequency, but they're different in intensity. Okay, that's this wrinkle on the top of page 4. And now you can think of the analogy of an elephant and a mouse. Because 90 dB SPL you can think of as an elephant. It's way more pressure than 80 dB SPL is because of those stupid logarithms again. So compared to 90 dB SPL, 80 dB SPL is a mouse. So if you add an elephant plus a mouse together, what do you basically have? An elephant. So 90 dB SPL plus 80 dB SPL is basically 90.0009 whatever, some tiny little thing more than 90. Okay, so 90 plus 80 is basically 90. 40 and 50 is basically 50. But that's if the decibel differences are at least 10 and more. But if you get a little bit, if you're adding 45 and 50, now the decibel distances are only different by 5, let's say. So if the differences in intensity are less than 10, that's where this weird little table came into the picture. Okay, so when you're looking at this PowerPoint slide, now looky here for an example to add 85 to 90 dB SPL. Okay, to find first of all, find the difference between the two numbers. In this case, it was 5. Then you go down to the curve, and you work your way leftward, and you'll end up at about 1.2. So 85 plus 90 dB SPL, find the difference between the two numbers, find that difference and on the curved line, follow the point leftward horizontally to the vertical axis. Note in this case, it intersects at 1.2, so you're going to add 1.2 to the larger of the 2 dB values to get 91.2. But notice, once there is no difference, look at the 0 at the top. When there's no difference, what does adding the two together correspond to? An increase of 3. And that's the most important thing to take home here from that too, because in real life you're almost never adding two identical sounds together. One machine in a room making 90 dB SPL and another machine in the room making 90 dB SPL. Just assume that the sound is going to be slightly different between the two machines. Even if they're the same machine made by the same company, hey man, one's closer to the wall, it's going to have slightly different reverberations, whatever. The sound is going to be a little bit different. And if it's any way different, doubling the sound pressure does not go up by 6. On the contrary, it goes up by 3. And that's the most common thing to remember. And that's how we're looking at this picture here. All right, good enough. And you flip over to the last page, just about the last page here. You're on page, let's see, where are we now? How far have I gone? 1, 2, 3. Oh yeah, that was page 3. And now we're at the top of page 4. And working on, middle of page 4, relative and absolute dB values. Okay, put a star by that. Very important. Relative and absolute dB values. Make sure you know this one, because this one's big in our field called hearing aids. Huge. We do this all the time in hearing aids. And that's what you're going to be doing, is fitting hearing aids. So it behooves of us to make sure we've got a grip on this one right here. Absolute is any decibel value that is referenced to the ground. So let's look at the ground here on this slide. Any of these decibel values on this vertical axis are absolute values. What does that mean? They are all related to the ground of 0. We defined what 0 was. It was the softest it took for a normal hearing human to hear a 1,000 hertz tone at 1 meter distance from a speaker with 2 ears. Okay, that's the ground. That's holy. Let us put a shrine by it. So everything is now related to that ground. Okay? To say an apartment is twice as tall as a house, we got to know where the ground is. Good. So now that we've defined that, so we'll say every decibel, SPL, is an absolute decibel value. I'm on the West Coast. The time for me is 9:45 right now, okay? That's because I'm relating it to Pacific Standard Time. In Springfield, Missouri, it's 11:45 noon. You're 2 hours ahead of me. That's because your ground is Central Standard Time, okay? But if I say the word 2 hours, that's a relative value. 2 hours doesn't mean anything. 2 hours can be added to 12 to your time in Central, or it can be added to my time here. So the phrase 2 hours when you're talking time is a relative value, whereas 4 p.m. or 6 p.m., those are absolute values because they're related to the anchor of your time zone. So what's 4 p.m. plus 6 p.m.? I don't know, it doesn't make any sense. I can't add two absolute values like that together. It doesn't work, okay? But what's 4 p.m. plus 2 hours? 6. What's 6 p.m. plus 2 hours? 8. All right, let's take it home to hearing aids, because decibels, like time, is also absolute and relative. So here we go. As we've seen, we cannot simply add 2 dB SPL values, put SPL values, write that down, together like 1 plus 2 is 3. If each one is an absolute value, referenced to the ground, you can't add them like 1 plus 2 is 3. So 90 dB SPL plus 90 dB SPL is basically 93 dB SPL. Okay? But hey, 93 is more than 90. So what was my gain there? What was my increase? 3. So 90 plus 3 is 93. So in some ways I can add decibels, can't I? Take it home to hearing aids. Input plus gain is output. Input is the sound waves hitting the hearing aid. Gain is what the hearing aid is adding to it. That's a relative value. And output is the sound coming out of the hearing aid's little speaker and hitting your eardrum. So input is dBSPL, gain is dB, output is dBSPL. So if I'm adding an absolute and a relative decibel value, I can, C-A-N, capital letters, underlined, bold-faced, I can add like 1 plus 2 is 3. And yay, yippee-you-da-day, that's what we do in our field every day. Okay? So in our field, we get our dessert. We get the ice cream. We get to add decibels like 1 plus 2 is 3, but put a caution by that. It's only when you're adding an absolute and a relative decibel value together. Let me make it plain. Pretend my input is 50 dB SPL, which is like soft speech, 50 dB SPL. And if the hearing aid is adding 50 decibels of gain, my output is 100 dB SPL. What if my input is 60 dB SPL? And my gain is 50. Well, then my output is 110. What if my input is 70 dBSPL and my gain is 50? Well, now my output is 120. Okay, see how gain is relative? 50, 50, whatever, it's always 50. If my gain was 10, then it would have just, the 10 is relative. I can add that 10 to any input. Okay, so input to a hearing aid and output from a hearing aid are always dBSPL, absolute values. Gain is a relative value, and that gain, whatever it is, can be added to any particular input, like 1 plus 2 is 3. And thank goodness, see, we're not walking around in factories measuring sound intensity with sound level meters. Okay, that's what people do who work for occupational safety and health. We don't. In our field, we're fitting hearing aids. So in our field, we get to add decibels as long as they're inputs and outputs and gain like that. Good stuff. Working our way down page 4, make sure you put a star by this one too, because we should know what basic decibel levels are for a whisper, conversational speech, okay, all that good stuff. So here you go. Typical sound levels, make sure we've got this down, okay? Make sure you know that, because now we have to talk about noise-induced hearing loss. Noise-induced hearing loss, and that becomes our specialty. What's the second most common cause of hearing loss? After aging, after presbycusis, which is hearing loss due to aging, which is the #1 cause, the second most common cause of hearing loss is noise. Okay? So a soft whisper, 40 to 45. What's ambient room noise? Write that in your margin there. Ambient room noise, 35 to 40 dBSPL. So you can tell that our ears are never sitting there listening to 0 or 10 dBSPL. That's only in experiments. Our ears are always getting some sound, okay? And ambient room noise with nobody talking is around 35 to 40 dBSPL. Average conversational speech, 60 to 70, 50, 65 to 70. Look where I've highlighted there. That's a biggie. That's an important one. Average, because that's what people want to hear who are wearing hearing aids. Okay? Yelling or shouting, 80 to 90. Lawnmowers, 100 plus. Jackhammers, 120. The threshold of pain is around 140. You'll see at the bottom of page 4 something called inverse square law. Don't freak about that one. Just put FNO, freak not out, or put for nerds only. But basically realize, obviously, as you go further away from a sound, it gets softer. Duh. So basically it means if you've doubled the distance from the sound source, it says you go down by about 6 dB. But that's only in a perfect free field of sound. Almost never is it exactly like that, because you've always got things that sound is bouncing from, like trees and walls and roads and whatever. So basically the inverse square law says if you double the distance from sound, you go down by about 6 dB. Enough on that. All right. Instrumentation that measures in decifrickin' bells. Okay? Excuse me, sound level meters. Sound level meters. Let's take a look, see if we've got a picture of one of these guys. Sound level meter. Go down here. If I've got a picture of a sound level meter, here you go. Sound level meter. Okay? People walk around with sound level meters. This is how sound level meters are calibrated. Don't worry about it, but here's another sound level meter. Here's a dosimeter measuring exposure over time. Okay, but basically the idea behind sound level meters is, don't worry about this slide, it gets kind of strange, but when you see dBA, and you see, and the measurement of the sound was 85 dBA, that means that they measured with a sound level meter. And it means that they cut off a bit of the low frequencies because we don't hear the lows quite as well. That's all that matters. Just all I care about right now is that you know when you see dBA, it's talking, oh, they were measuring noise in a factory. That's all I need you to know. Basically, look what noise does to your inner ear. Is anybody watching this video, if anybody's watching this who takes anatomy 120? Or have you learned anything about hair cells in anatomy? In your anatomy 120, noise-induced hearing loss. Look at this guy where I'm tracing here. I'm going to blow it up so you can see it a little bit better. The X's are his left ear. This is an audiogram. It means he's got great hearing for his left ear for low frequencies, mid frequencies, and all of a sudden, boom, a big hearing loss in the highs. Huge. And that's because his hair cells are normal, and all of a sudden, boom, gone. Noise kills off hair cells, and noise kills off high frequency hair cells. Noise causes a high pitch hearing loss that's permanent. And it's really weird in hunters who use rifles, okay, if I'm right-handed, it's my left ear that's closest to the barrel. So this is hair cell count from a hunter who was right-handed. And you can see that the right ear, the inner hair cells aren't damaged very much. The outers are a bit damaged here. But his left ear is worse. His left ear, the hair cells are totally dead in the high frequencies. These dotted lines are the rows of outer hair cells. The solid one is the row of inner hair cells. Anybody taking anatomy will have seen that, but at any rate, just giving you an idea. It's interesting that right-handed hunters will have worse left ear hearing, and left-handed hunters will have worse right ear hearing, especially if they're using rifles. Anyway, basically, it's kind of a weird topic to talk about given Florida, what just happened, but at any rate, stop needless noise, okay? You've got a cop here saying, help keep America calm. Elderly people in Africa have better hearing than elderly people in USA and Canada. And the reason why is because Africa has less noise pollution, less industrial noise. Our ears were meant to hear soft voices over the crackling of a fire. Our ears were meant to hear the roar of a lion way off in the distance. Our ears were never meant to hear the clanging of steel on steel. Noise-induced hearing loss is the second most common cause of hearing loss. This is what a hearing test looks like from someone who's been exposed to noise. It's permanent. Good hearing, X's and O's, not many decibels required to hear the low to mid frequencies. It's at 4,000 hertz especially that the hearing loss is most prominent. And then at 8,000 it gets better again. This is the earmark, so to speak, of noise-induced hearing loss. Okay, really take that home and look at this is how you can tell as a hearing instrument specialist. You can tell right away, yeah, it's noise-induced loss. I can just tell by looking at the shape of the hearing loss. Normal presbycusis, aging hearing loss, follow my cursor, goes down like a goes down, follow my cursor like a slope, like a hill. Okay, better hearing in the bass, worse hearing in the mids, worse in the treble. Kind of goes down like a regular slope of a hill. Noise-induced has that notch out of it, like a rat came in like a thief in the night and took away some of your hair cells. So I'm just kind of scooping around here. Let's look. Exposure time limits. Take the slide home. This is a good one. And it deals with your notes as well. So if we look at our notes, hit escape, look at our notes, put a star by this, right there. Okay, what is your noise exposure allowance? What are you allowed to have in terms of noise exposure? You're allowed to have usually about 85 to 90 dB SPL for 8 hours a day. Note the two things. One is the cutoff, and the other one is the time of exposure. So most states and most provinces in Canada, okay, the cutoff is 85 dB SPL for 8 hours a day. If you increase the decibels by 5, your allowed time exposure is now only 4. So let me show you on the picture here. If the cutoff is 85 decibels for 8 hours a day, if it's, here they're saying if it's 88, it's now 4 hours a day. If it's 91, it's 2 hours a day. See, they're being stricter. They're saying for every increase of 3 dB, your allowed time exposure is cut in half. What I want you to take home is basically round it off. Say that the cutoff frequency is about 85 dB SPL, and if you increase that by 5, your time exposure gets cut in half. So if I say 85 dB SPL is allowed for 8 hours a day, and then I say on a quiz or a test, what's the allowed time exposure for 95? Well, you'd have to go 85 for 8, 90 because I went up by 5, now my allowed time exposure is 4 hours. And if I go up by another 5 to 95, now I'm down to 2 hours. So the correct answer would be 2 hours. Okay? So that's what I need you to know. Some states, it's 3-hour increase. Some states, it's a 5 decibel increase or whatever. What I need you to know, basically hold the anchor of 85 and 8 hours a day. And as you increase your decibels by 5, your allowed time exposure goes down by half. Okay, that's the general rule of noise-induced hearing loss. We're on that last page. Let's look at some types of earplugs that people use to protect themselves from excess noise. Now, let's take a peek here. And let's look at some bogus decibel values too. Let's look at this so we can take this unit and finish it. Here's a picture, a slide, that's wrong. Okay? This picture isn't true. 0 decibels is not the faintest sound heard. Oh, that is the faintest sound heard by a human ear. Yeah, but they're missing. They should call it dB SPL. But what's wrong here is the 30. Whisper in a quiet library? I don't think so. Ambient room noise is 35 to 40. A whisper is about 50. Okay? Average conversational speech, 65 to 70. So this is kind of a little bit too low. These are more realistic now. 90 and 100, 115 and 140. Those are more realistic. But these two here I have a little bit of a concern with, especially the 30. If you look at this, here's another picture. They should be calling this dB SPL. They're not, but they should. Okay? Just audible sound, okay, 0 dB SPL. The soft rustle of leaves, I don't think so. There's more than 10. A whisper at 4 feet, are you kidding me? That's about 50. Okay? A quiet street in the evening with no traffic, why not say ambient room noise is about 35? So I find this one a little bit off the track too. It's just, I like to show people, these are from common magazines that people buy, and they're not always true. Okay, but get the general gist. Look at 80 plus, and you start getting into noise-induced hearing loss. Basic conversation at 3 feet, that's correct. 60 to 70 dB SPL, that's correct. That makes sense. But these down here are a little bit off the chart. Here's another one, hearing threshold at 0 dB. They should call it 0 dB SPL once again. Breathing at 10, I don't know. Whispering in the ear, 15, I don't think so. Those are wrong, okay? A very quiet library, maybe 30, but usually ambient room noise, 35 to 40. And then they start getting into normal conversation, 60 to 70. That makes sense, okay? And then the rest of these are, well, whatever. How do they know what a clarinet and an oboe is? 92, at what distance? I don't know. Again, it's just, how loud is it? There you go. Music, firearms. This one's quite true. Okay, look at the dBAs. See how it says dBA? That means that they walked around with a sound level meter. That's how you should really think about it. But it kind of gives you an idea of what's going on. Okay, this one's fairly, look at the toy box. Toys can cause noise-induced loss in children, in babies. They can. Some toys have been taken off of the market because of that. Audiologists have found that sometimes some toys that are sold by Mattel or whatever, toy makers, are really quite noisy. Firearms cause noise-induced hearing loss. Music causes noise-induced hearing loss. Ask Eric Clapton and some of these rock and roll singers. They're now hitting their 70s. They're going in for hearing aid testing, hearing testing. They're losing treble, they're getting noise-induced hearing loss from all the music they've listened to. Okay, basically another thing that talks about noise that's really intense. Look at a rocket launch from a pad, 180 decibels. That'll be an eardrum blower outer. All right, again, just giving you all kinds of things, but basically the cutoff is around 85, level at which hearing damage begins for 8 hours a day. Normal conversation, 60 to 70. Quiet office, look at that, they're saying 50. Basically, remember, ambient room noise, 35 to 40. A whisper, about 50. Average conversational speech, 65, 70. Yelling, 80 to 90. The cutoff for noise-induced hearing loss, 85 dBSPL for 8 hours a day, etc., etc. All right, basically, here's types of earplugs. If you put cotton batting in your ears, how much does it attenuate? Look at the word attenuate. That means to quiet. Okay? When you see the word attenuate, that's the opposite of turning up the volume. How much do these earplugs quiet? And you can see that cotton batting stuck in your ears doesn't quiet down the low frequencies very much, 125, it hardly does anything. And then as you get to the highs, it might cut off about 10 dB. And then look at the bottom one, foam EAR plugs. And I'm going to pull out something that you might see. Yeah, here we go. A foam EAR plug, a foam plug. A plug looking something like this. One of these yellow, spongy things. I'll stop sharing, just let you see it a little bit better. Okay? One of these plugs. Now, this one's got a hole in it, but you know what I mean. These ear plugs that you find. Okay, this one's connected to a tube. That's because it used to be on a hearing aid. Don't worry about it. I'm just kind of pointing out the sponge. Those types of earplugs, go back to the screen, attenuate by about 30 to 35. And then in the high frequencies, they really knock out the sound. Now, what do you think that's going to do for the understanding of speech? Because in speech, the most important sounds are the consonants. The letters S, Sh, F, S. If you think of the words fat, hat, sat, cat, they all have but doesn't mean much. It comes from the throat. It's loud and it's low. It's a vowel. And we have 5 vowels, and every one of our thousands of words in English shares those 5 vowels. What makes those words different is the consonants. Sh, fat, cat, sat, bat, hat. And those consonants, the lip sounds, are high frequencies. So when you're wearing earplugs and you want to block out sound and you use a foam earplug, you're knocking the stuffing out of the consonants. So that's great if I'm working with a circular saw and I'm outside doing construction. Well, I'm not trying to talk to anybody anyhow. So good for me. Okay, I'm blocking my ears from noise-induced hearing loss. But I can't communicate with other people very well. That's okay. I want to protect my ears. I'm alone and I'm working in the garage, so I don't care. Okay, but if I'm a musician and I want to hear the fidelity of music and I want to hear it right, okay, then I'm going to buy a musician's earplug, because a musician's earplug is going to block out all the sounds evenly by about 15 decibels. Musicians' earplugs are really weird because they block out. You can block out by 9 or 15 or 25 as compared to a foam earplug. Notice the attenuation is kind of flat. You know why it's kind of flat? Because your ear canal resonance. Now remember this and remember it well. Your ear canals are like a cup. They're open at one end, closed at the other end. And all those kind of shapes resonate. Okay, they all have a and your ear canals resonate with high frequencies. Your ear canals naturally resonate with 3,000 hertz, which is right where the consonants are. This is the natural, unprotected, open ear canal resonance. Okay? When you're wearing musicians' earplugs, they preserve that resonance. They just lower it down. And that's why your attenuation with musicians' earplugs is nice and flat. And guess what? You get what you pay for. Foam earplugs cost about 50 cents. Okay, musicians' earplugs cost about $50. Okay, you get it? So you get what you pay for. Musicians who want to hear each other speaking while they are playing their instruments usually wear musicians' earplugs. And that's what you may very well be making in your clinic. You're going to get clients coming to your office saying, I want swim plugs for my kid. And then again, you might, those will be cheap. Okay? Then again, you might be someone then coming in and a person plays guitar and says, yeah, I've heard of musicians' earplugs. And you'll say, so have I. I'll make them for you. You're going to take the ear mold impressions of the guy's ears, and you're going to send those ear mold impressions to the factory to be made into musicians' earplugs. And the musicians' earplugs will be sent back to you, and you'll be calling up the person to come in and get fit with his musicians' earplugs. And then you're going to charge the person about $100. Okay? And that will be nice, tidy lunch money. All right? So you're not only fitting hearing aids in this field, you're also taking ear mold impressions for lots of different earplugs. For people who want noise protection, for people who want water protection against their ears when they're swimming, for people who are bugged because their spouse snores in bed and they want earplugs made, okay? Who knows? But you're going to be the person taking the ear mold impressions, making that happen. And I wanted to share that with you. That's a great way to end Unit 2 when we're talking about this here is just a stupid name, don't worry about it. So basically, this is now basically reaching, here's the loss of hearing. Okay, here's where your speech sounds are. They call this a speech banana on a hearing test. Low C 125, middle C 250, high C 500. This is an audiogram with decibels going down the side. And they're showing you regular conversational speech. And on the right-hand side, you can see where the person has had hearing loss in the highs and therefore cannot hear the consonants of speech. And that's why the elderly always say, you young people mumble. Young people mumble. Well, that's mumbling is like cutting off the high frequencies of speech, and now the person can't hear the highs very well. So what hearing aids have to do is to take that frown and they have to turn it upside down and really deliberately increase the highs because the person can't hear the highs very well. So most of your amplification is treble. You're mostly going to be amplifying treble. And that's why hearing aids are programmed. They're programmed to deliver the right kind of sound for the person's hearing loss. And you will be programming the gain of the hearing aid. Are you wanting most gain for the low frequencies or for the mids or the highs? Well, that depends on the person's hearing loss. And you'll be entering the hearing loss in the computer, and then you're going to be connecting the hearing aids to your computer by Bluetooth, and you're going to be programming the hearing aids to provide a mirror image of the guy's hearing loss. And in that wise, you are prescribing hearing aids. And in that wise, I can't wear your hearing aids any more than you can wear mine, just like glasses. These are right for me, they're not right for you because my vision's different from yours. Okay? Just like lenses take a prescription, so do hearing aids. And that's what the lay public doesn't get. They all think, oh, hearing aids make sounds louder. No, they are sculpted. Deliberately, you are shaping the frequency response of the hearing aid so that its gain and its output are servicing the person correctly according to his or her hearing loss. Now, let's leave Unit 2. Let's just kind of go away from it. Unit 2 is now basically done, and I want to take you to Unit 3. So I'm going to escape out of here. I'm going to shrink this down. I'm going to shrink this down, and we will go and look at the other units. Now, do you see what's on my screen here? We've covered frequency, wavelength, speed of sound. You've had your PowerPoint and your notes. We've covered intensity and the decibel, notes and PowerPoint, and now we move into complex sounds and speech. Let's talk about complex sounds and speech. And I'll pull up this picture right here, and we'll kind of start way at the very end, the last slide, because we'll spend 2 to 3 weeks on this unit. But I'm deliberately carrying on from where I left off in Unit 2. Here's another hearing test. Looky, looky. The X's are the left ear, the O's are the right ear, and 0 decibels is a line drawn at the top. And the numbers at the very top from left to right are hertz. 125 hertz, 250 hertz, 500 hertz. It really hurts. As we double the numbers, we go up 1 octave, right? So we test hearing at 7 octave frequencies. Remember that? From way back in Unit 1. And we test the decibels required for the person to just barely hear all the different frequencies. And this is typical presbycusis. So the good hearing in the low frequencies, not many decibels required to hear under headphones. Did I hear that? But as I get higher in frequency, it requires more and more and more decibels to hear. So this person has trouble hearing treble. He's got trouble with treble, okay? And look what the outer ear does, your outer ear canal. Here's my cup again. Now, I'm not going to turn it too much or I'll spill coffee on my keyboard, but you know what I mean. Here's a cup. It's like a cylinder. It's closed at one end, open at the other end. That's the same as your ear canal, okay? And your ear canal is therefore called a quarter wave resonator. It's going to vibrate or with sound waves that are 4 times its length. Why? Because it's shaped like a cup. That's why. Okay, now, how long is your ear canal? 1 inch. Come on north of the 49th parallel into Canada. Leave Trump country for a second, come north. What's the length of your ear canal? 2.5 centimeters. Okay, 2.5 centimeters is 1 inch. Good. It's going to vibrate with sound waves that are 4 inches long or 10 centimeters, because 4 times 2.5 is 10. And what's 10 centimeters? It's 1/10 of a meter. Ah, wavelength is speed of sound over the frequency. Wavelength, 0.1 meters equals speed of sound, 340 meters per second over x. Okay, 0.1 over 1 is equal to, and now I'll draw on my paper here and show you. 0.1 over 1 is equal to 340 over x. I will share with you to figure out what frequency. 0.1 over 1 is equal to speed of sound over x. Okay, wavelength is equal to speed of sound over frequency, and we want to know what frequency is. Remember that from Unit 1? Good. So we know the wavelength. Here now we're trying to find the frequency. Well, let's cross multiply. 1 times 340 is 340. 340 divided by 0.1, get your calculator out, and it's going to be 3,400. So your ear canal is naturally going to vibrate with 3,400 hertz. But your ear canal ain't glass, and your ear canal isn't steel. Your ear canal is made out of flesh and bone. Therefore, that resonance is spread out. And that resonance, instead of being 3,400 hertz, is now kind of a and looky. From about 1,500 hertz all the way out to past 4,000 hertz. You get about a 20 decibel increase. So look what your outer ear canal is doing. with its resonance. It's increasing the audibility of the high frequency consonants. All right? Because look at the orange letters. The orange letters are literally the letters of speech superimposed on the audiogram. So when you say the letter Z, Z, V, V, put your hand to your throat and say those. You're always using your voice. J, M, D, B, I, U, L, R. All those sounds are loud and low. But when you get to P, Ch, Sh, K, F, S, you're softer and higher. So your ear was made, whether you believe in creation or whether you believe in evolution, your ear is made to match for speech. If we didn't talk, our ears would look like dog or cat's ears. But because we are an animal that talks and we use vowels and consonants, we must hear those highs. And the outer ear is naturally resonating with high frequency consonants. So that's really, we take it home that way in Unit 3, because in Unit 3, we're talking about the most important complex sound on Earth, speech. Okay, because that's a complex sound. What the Sam Hill is a complex sound. So let's go to the very beginning of this PowerPoint here. I'll take it all the way home. And you're going to look at a picture you saw in Unit 1, way back in Unit 1, before we talked about the decibel from hell. And we said there's two ways to represent sound. We said one way was sound waves, period, wavelength, blah, blah. The other way was a spectrum. Remember that? And a spectrum, the horizontal axis is frequency, and the vertical axis is no longer, it's amplitude. So whereas a wavelength, a sound wave, amplitude over time, or amplitude over wavelength. Okay, here it's different. Here it's amplitude on the vertical, frequency. And look at all the different sounds. You see, we almost never hear simple sounds. Most sounds we hear are complex. And that's the title of Unit 3, complex hearing. Sounds. Complex sounds are sounds that have more than one frequency. Well, speech has thousands of frequencies, okay? Music has lots of frequencies. Traffic noise has lots of frequencies. So every sound that you hear in your daily living and environment is a complex sound. And the definition of complex sound is more than one frequency. So here's a spectrum showing you a complex sound. And you can see that the complex sound has buku frequencies. Here we'll call this one has 100 hertz, 200 hertz, 300 hertz. In this particular example, this is the fundamental frequency. It's the lowest one. And then the other ones are harmonics, equal multiples of the fundamental frequency. And you can see that in this particular example, not all examples, just in this particular example, most amplitude is for the low frequencies, and gradually less amplitude occurs for the higher frequencies. That's just that particular sound. Here's another picture showing you a simple sound and another simple sound. These are pure tone. Here's a tone. Well, I don't know what frequency it is. It'll just whatever. Of course, you know, to figure out the frequency, you know what you'd have to do, wouldn't you? You'd have to know what length of time this is, and then how many bumps occurred per length of time. Oh, well. Anyway, here, and another simple sound. So this one's the lowest frequency. This one's a slightly higher frequency. This one's higher in frequency, but it's softer. Anyway, you add those three sounds together, you're going to get the bottom, a complex sound. And you're looking at the waveform. These are not spectra. This is a spectrum. These are sound waves. Spectrum, sound waves. Okay? Two ways to represent sound. Okay, now looking at this picture here, almost all sounds we hear are made up of additions of lots of sounds together. So lots of, you add this tone, this tone, you'll have a complex sound. Now look at that sound wave. Do you see a pattern to it? I do. It's kind of ragged, but it's still it's still going up and down. As long as you can still see a pattern, it's going to sound tonal. It's going to sound, but if it has no pattern, okay, let's look at a sound wave. I'm moving ahead here. Look at this waveform on the left. Do you see a pattern there? I don't. It's just a ragged bunch of junk. That's called noise. Noise is not tonal. It might be a radio between stations. Could be a waterfall. Could be traffic. Okay, it's noise. Noise does not have a waveform that repeats over time. Noise, it has what they call an aperiodic waveform. Aperiodic means it's spelled aperiodic, non-aperiodic. Okay, it has no rhythm. I cannot see a pattern. Well, then, buddy, it's noise. And that's the physical definition of noise. Any waveform that has periodicity to it, when you look at the bottom one in this slide here, it's a complex sound, but I can see a pattern. It's going to be tonal. Okay, so the bottom one might be the vowel A, E, A, O, U, could be a vowel, whereas this might be, whoa, S, Sh, K, consonants. Consonants are noise. Speech is it's a complex sound that has a combination of tonality, vowels. All sounds from the larynx are complex and they're tonal. In other words, their waveform will have a ragged appearance, but it'll be repeated. Whereas all sounds from the lips are high frequency batches of noise. So when you think about speech, we often put too much meaning on it. If you strip the meaning out of speech, then you're hearing just its acoustics. And that's what you as an HIS need to learn, is the acoustics of speech. And to best appreciate that, go on a subway in a big city and listen to people talking in a language that you don't understand. That's the best way to get what I'm talking about here, because then you don't know what it means. All you're hearing is the sound, and that's how hearing aids are. They're as dumb as a stick. They don't have a brain. They're just processing the sound of speech. They have no idea. They can't care less about the meaning. So that's why you as an HIS, we need to learn the acoustics of speech, and you marry that with hearing aids. Input plus gain is output. The acoustics of speech, vowels being louder and lower and more tonal, whereas consonants are softer, higher in pitch and noise. Okay, so speech is a complex sound made out of tonality and noise. Bits of both. Okay? Music is mostly tonality. Speech has less tonality than music does, of course, but it has some tonality in terms of the vowels. So that's really what I wanted to take you through here. And we're near the very end. What I'd like to do here is just pull up the notes if I could. So I'm going to pull up the notes to this and look at complex sounds in speech. Okay, now we're pulling this up here. Once it pulls up, look at the notes. Look what we said. Almost all sounds are complex. They can be periodic or non-periodic or a mixture of both. Periodic sounds have a sound wave that repeats over time. Any sound wave that repeats over time is tonal. Up until now we've discussed tones, but pure tones hardly exist in nature. The only time you hear pure tones is in a hearing test, under headphones. in a sound booth. Walk out of the booth into regular everyday life, and you're smitten with complex sounds. And now we have the second section, spectrum versus waveform for representing complex sounds. And so you will read the limitations of each. Okay, sound takes place in frequency and intensity over time, but a piece of paper has only two dimensions, length and width. So I need two different ways of showing sound. Okay, I need sound waves and I need spectra. And a sound wave, time, amplitude, spectrum, frequency, amplitude. Amplitude is spoiled. It gets represented in both, and it's always the vertical axis. So waveforms are great at showing you tiny changes over time, but waveforms absolutely suck at telling you what the sound was. Look, if I go to here, what's the frequency? I don't know. What's the frequency of any of these? I don't know. I'd have to figure out what the length of time was from here to here, and then count the wavelengths, and then I guess figure it out. Okay, so waveforms aren't very good at telling you what the frequency is, but spectra are. A spectrum is fantastic. When you think of a spectrum, remember what I said in Unit 1. It's like a slice out of a loaf of bread. Think of sound waves as being a loaf of bread from this butt to that butt, starting here, ending here. And a spectrum is when you take a knife and you take a slice out of the bread and you turn it sideways to see the raisins and the oats. Okay? Because now I can see what's in the bread. So a spectrum is fantastic at telling you what was in the sound. There's a spectrum. But it's as a time. Look at time isn't even represented there. It's a slice. Okay? So a spectrum is wonderful at showing you what frequencies are in the complex sound. Waveforms, however, are much better at telling you changes over time that take place in a complex sound. So they have their strengths and their weaknesses. We're almost done here. Okay, so you'll read on down here, and next week we will pick up on this big time. We'll talk, I'll give you a spectrum. Oh, here, fundamental frequency, the lowest frequency in a complex sound. And there's the harmonics. Okay, da-dee-dee-dee, da-dee-dee. You've heard some of this. We're going to be revisiting resonance again next week. Okay, we'll be talking about noise next week. We'll be talking about waveform and spectrum for broadband noise, because looky, noise is kind of strange. I'm almost done here. Here. White noise, pink noise. White noise and pink okami noise. Okay, what the Sam Hill does that mean? White noise has, look at this, the spectrum is flat. It means it's got energy at all the different frequencies. And instead of drawing thousands of little white lines going up and down to show you all the frequencies in white noise, they just draw a line straight across. White noise has all frequencies at equal intensities. Pink noise is more like speech. Look at pink. It's got lots of energy in the lows, but as you go higher up in frequency, the amplitude decreases. And that's just like speech. You want to see the spectrum of speech? Here's the spectrum of speech. And look at how it has more energy in the lows than it does in the highs. So this is a spectrum of the overall sounds of speech. The vowels, louder and lower, and as you get to the high frequency consonants, that you get less and less amplitude. And of course, speech fluctuates, so I'm showing you a bit of a range. But basically, speech spectrum is much like pink noise spectrum. Okay? So white noise, pink noise. What would white noise sound like versus pink noise? White noise, pink noise. They're both not tonal, but hey, they sound different. Okay, one waterfall, big waterfall. They're both noise. but they have different spectrum. They both have sound waves, but you can't see a pattern in them. They're not tonality, but they still sound different. But we'll talk more about that next week. All right, so today we've kind of looked back at Unit 1. We hooked into some formulas there, and then we did that because we wanted to end the session with an introduction into Unit 3, which kind of harks back to Unit 1 a little bit. Only in Unit 1 we were talking about simple sinusoids, pure tones, wavelengths, frequencies, speed of sound, blah, blah, blah. Now we're talking about real life. We're kind of going back to that a bit, but we're talking about complex sounds because that's what we normally hear with our ears. But in the middle between those units, you had to cover the decibel from hell, and we reviewed and covered some of that and finished off that unit as well. Jumping off from the end of that, about noise protection, and the most important sound is speech. We launched off into Unit 3 to talk about speech a little bit and complex sounds. All right, it's time for me to take this out, put it on something, and grab a coffee. Anybody have any questions? Don't hesitate to email me. Otherwise, it has been a slice, a spectral slice. Cool, a thick one. Adios. Catch you later.